Section 5.3, the binomial probability distribution. In the previous section, 5.2, we talked about probability distributions in general. What we're going to do in this section is look at a specific situation that results in what we call the binomial probability distribution. A binomial probability distribution results from a procedure that meets all of the following requirements. Number one, the procedure has a fixed number of trials. So that fixed number could be 10, or it could be 100, or it could be 1,000. Whatever it is, it has to be fixed, not changing. Number two, the trials must be independent of each other. So for example, think about flipping a coin. If we flip it 100 times, each flip is independent of any previous flips. Each trial can have one of two outcomes. So in the in the coin example, we can either have head or tail come up in each trial. And number four, the probability of success is the same in each trial. So with the coin example, if it's a fair coin, the probability of getting a success would be 0.5. Now it's important to realize that term success can be used fairly loosely, meaning that we could have called getting a head a success, or we could have called getting a tail being a success. In either case, we have to choose one of them to be a success, and the other one we'll call a failure. But that doesn't necessarily mean one is good and one is bad. We're just distinguishing between the two possible outcomes. The random variable for a binomial distribution could record the number of successes. Let's take a look at this example and ask ourselves, does it result in a binomial probability distribution based on the four criteria that we just looked at? So in a drug trial, if 800 subjects are treated with Lipitor, doctors record a yes if the subject gets a headache within 24 hours and no if they don't. Based on Lipitor's claims, there is a 10% chance that someone will get a headache after using the drug. So we first have to ask ourselves, were there a fixed number of trials? And in this case, if we consider each of the subjects to be a trial, there were 800 trials. Are the trials independent? Well, if one person gets a headache, you have to ask yourself, would that affect the probability that somebody else would get a headache? And of course, in this case, no. Then we have to ask ourselves, does each trial, each of the subjects, have one of two possible outcomes? Either yes or no in this case. So there are only one, you can only have one of two possible outcomes for each person or each trial. And lastly, ask ourselves, is the probability of success the same in each trial? So first of all, let's define what the success is, or what we'll call success. We'll call getting a headache a success, in which case the probability of a success would be the 0.1 or 10% that Lipitor claims. So the probability of getting a headache will be the same thing as the probability of success. So again, keep in mind, success does not necessarily mean it's a good or bad thing. You just have to pick one of the two possible outcomes to be a success. So we'll choose yes to be a success, and no will be what we'll call a failure. So let's take a look at another situation. Giving 800 subjects a dose of Lipitor and asking them how they feel. So going through the four criteria, there were a fixed number of trials here, 800. The trials are again independent because how one person feels doesn't affect how another person feels. Does each trial have one of two possible outcomes? Well, if we're asking them how they feel, you can imagine the array of different responses that we'd get. Somebody might say, I'm feeling good. Somebody else might say they're feeling bad. Somebody else might say they have a headache. Somebody else might say they're feeling tired. There are not only two possible outcomes. There are many, many possible outcomes. So, because that doesn't fit the criteria, this would not result in a binomial probability distribution. Another situation. Treating 152 couples with a fertility treatment and recording whether they have a boy or a girl. So here they have a fixed number of trials. The trials are independent. Whether if somebody has a boy or a girl, that won't affect the next child that is born. Each trial has one of two possible outcomes, either a boy or a girl. And lastly, the probability of success is the same in each trial. So we would say that this results in a binomial distribution. One more situation. What if we asked people if they are registered Democrat and stopping when you found 20 people who say yes? So we're going to poll people on the street and ask them if they're registered Democrat, and then we'll stop only when we've found 20 people who say yes. So ask yourselves, was there a fixed number of trials in this situation? But since we don't know how many people we'd have to ask before we found 20, there are not a fixed number of trials here. There could be 100 different people we have to ask before we get 20, or there might only be 22 people before we get 20, or there might be 20 people that we ask before we reach 20. We just don't know. And so there's not a fixed number of trials, so we would say this would not result in a binomial distribution. But keep in mind, even though this might not result in a binomial distribution that we're talking about in this section, it may result in some other type of distribution. So example, an exam consists of multiple choice questions, each having 4 possible answers. Only one of those answers is correct. So suppose we had to guess the answers to 6 of these questions. What is the probability that none are correct? Now this is something we've done in previous sections. So if you imagine answering 6 of these questions, each answer is independent of any previous answers. So the probability that none are correct is the same thing as finding the probability that the first one is not correct, times the probability that the second one is not correct, times the probability that the third, the fourth, the fifth, and the sixth are not correct. So the probability that something is not correct, if you imagine there are 4 possible answers and only one is correct, then there's a 3/4 probability that we would answer incorrectly, or 0.75. So the probability that we'd answer none of them correctly is 0.75 times 0.75 times 0.75 times 0.75, or in other words, 0.75 to the 6th power, which comes out to be 0.178. So let's find the probability that at least one is correct. And again, this is something we've done in previous sections. The probability that at least one is correct, you'll remember, is 1 minus the probability that none are correct. And since we just found out the probability of none, we can say 1 minus 0.178, or 0.822, is the probability that at least one is correct. So what we'll talk about now, and this is new this section, we're going to find the probability that exactly 4 are correct. So we don't have the information yet, but to determine that, we'll need the formula for the probability of a binomial distribution. You may recognize the first part of this formula. This is what we talked about in the previous chapter that we called NCR, or N choose R. Here we're going to use X, but it's the same idea. So this would be, in the previous example, the number of questions that we're answering, or in general, the number of trials. The X, in the previous example, are the number of successes, or the number that we're going to get right, which we said was 4. But in general, just the number of successes that we're interested in. The P is the probability that on any one trial we'd get a success. And the Q is the probability of a failure. And we can usually, we can always calculate that by saying Q will be 1 minus P. So 1 minus the probability of a success will give us the probability of a failure. So using that formula, we can now answer the probability that that we answer 4 correctly. So the probability of 4 will be 6 choose 4 6 choose 4, times the probability of success, which will be 0.25, 1 out of 4, because there are 4 possible answers and only one of them is correct on each question. And we take that to the 4th power, times the probability of a failure, which is 1 minus the probability of a success. The probability of a failure to the n minus x, in this case the number of questions minus the number of successes. In other words, the number of failures. So 0.75 to the 2nd power. So plugging this all into the calculator gets us 0.0329 probability that we would answer 4 correctly. Interpreting this a little bit, this tells us that it's a fairly low probability that we would get 4 out of 6 questions correct if we were just guessing. Find the probability of getting exactly 3 heads when you flip 5 quarters. To answer this question, or in order to use the formula for the binomial distribution, we first have to make sure that this would result in a binomial distribution. So we have to ask ourselves the 4 questions to make sure this meets the 4 criteria. Are there a fixed number of trials? In this case, we're flipping a quarter 5 times. So yes, there are a fixed number of trials. The second question, second criteria, are those trials independent? Well, flipping a quarter is independent of any previous flip because the probability that we'd get a head or a tail is independent of anything that happened on previous flips. So the trials are independent. The third thing we have to consider is each trial going to result in only one of 2 possible outcomes? There are indeed only 2 possible outcomes, a head or a tail, and so each trial will result in one of those 2 things occurring. And the last thing we have to consider is the probability of success the same on each trial? And of course, flipping a fair coin like this, the probability of success, or what we'll call getting a head, is going to be 0.5 each time. So yes, the probability of success is the same, so we can use our formula for calculating the probability in a binomial distribution. So we're going to say the probability of 3 is 5 choose 3 times the probability of success, which is 0.5, to the 3rd power, the number of successes, times 0.5, which is the probability of a failure, or probability of a tail in this case, to the 5 minus 3, or 2, to the 2nd power. Now if you write this out, one way to calculate using this formula is to write out what 5 factorial means, divide by what 5 minus 3, or 2 factorial means, and times what 3 factorial means. And then cross off or do some division depending on what could cancel out. I've also gone ahead and plugged in 0.5 to the 3rd in my calculator and 0.5 to the 2nd in my calculator. So crossing off from the top and bottom of this fraction the factors that can cancel out, we see that a 3 can cancel out, a 2 can cancel out, and the 1s will cancel out here. You could also go ahead and reduce the 2 and the 4 so that you just have 5 times 2, but if you don't, that's okay. We'll complete that on the next step. So here I'd get 20 divided by 2. Multiplying the decimals together, I'll have 0.03125. Of course, 20 divided by 2 is 10, and now 10 times 0.03125 is 0.3125, probability of getting exactly 3 heads when I flip 5 quarters. In the US, 40% of the population has brown eyes. If you randomly pick 14 people, what is the probability that 12 of them will have brown eyes? So first of all, ask ourselves the 4 criteria for this resulting in a binomial distribution. 1, are there a fixed number of trials? So if we're going to consider each of the 14 people to be a trial, then the fixed number of trials will be 14. Are the trials independent? Well, if we randomly pick one person and see if they have brown eyes, that that will have no effect on if we pick another person randomly and see if they have brown eyes. So these trials are independent. Will each of these trials, or each of these people, have one of two outcomes? Well, if we're calling a success having brown eyes, then you either have brown eyes or you don't when we pick a random person. So each trial will result in either having brown eyes or not. So one of the two possible outcomes. So the fourth consideration is the probability of a success the same on each trial? Well, we're going to consider the probability of a success, or the probability of randomly picking someone with brown eyes, to be 0.4, because we're saying 40% of the population has brown eyes. So that probability will remain the same. So we can use our probability for the binomial distribution formula and say the probability that we'd have 12 people with brown eyes is 14 factorial divided by 14 minus 12, or 2 factorial, times 12 factorial. The probability of a success in this case was 40%, so 0.4 to the number of successes, 12, times the probability of a failure, or the probability that someone doesn't have brown eyes, is 0.6 to the second power. And this all calculates out to 0.0006. Now suppose we wanted to know the probability instead of randomly picking at least 12 people out of the 14. So in other words, we want to know the probability of picking exactly 12, or exactly 13, or exactly 14. 12, 13, or 14 people that have brown eyes. Well, to calculate this, we simply need to calculate the probability of picking exactly 13 people, also calculate the probability of picking exactly 14 people out of 14 people who have brown eyes. So the probability that we pick 13 people with brown eyes out of the 14 will be the same calculation, just replacing 12 with 13 now. And that calculates out to 0.00005. And similarly, we'll do the same thing for 14. The probability that all 14 people had brown eyes is 0.000003. I might have said too many zeros there. But regardless, in order to calculate the probability that at least 12 people out of the 14 have brown eyes, we now simply need to add up those probabilities that we just calculated. So adding all those up, we get 0.000653 probability that at least 12 of the 14 people had brown eyes. One quick note, we have to regard 0 factorial as 1 to make any of these calculations come out nicely. So you may have noticed in the last calculation we did, the probability that 14 of 14 people had brown eyes. If you do 14 minus 14 factorial and call that 0, you'll get 0 times a number in the denominator of a fraction. In other words, you'd get 0 in the denominator of a fraction, which is never good. So whenever you see 0 factorial, regard that as 1. So in other words, you may have calculated this. You want to make sure that this does not become 0 times 14 factorial, or 0 times anything. You want this to become 1 because it's 0 factorial. And 1 times 14 factorial is 14. Suppose we wanted to create a probability distribution for rolling a die 5 times and counting up the number of 3s. So when we talk about creating a probability distribution, what I'm speaking of is creating a table with all the possible number of 3s that could come up when we roll a die 5 times. So, of course, there is the probability, or the situation where we'd roll 0 3s out of 5 die rolls. You could roll a die 5 times and have no 3s come up. You could have 1 3 come up, 2 3s come up, 3 3s, 4 3s, or 5 3s come up when you roll a die 5 times. But of course, since we're only rolling 5 times, we won't have any more. So in order to calculate up all the probabilities, we'd have to use our formula now for the binomial distribution. Now, of course, you should double check that this meets the 4 criteria for resulting in a binomial distribution. Fixed number of trials, the trials are independent, there's only one of 2 possible outcomes in each of the 5 trials, and the probability of a success, or in other words, the probability of getting a 3, will be the same in each trial. So, assuming those criteria are all met, and they are, then we could plug 0 into our formula, or in other words, we would have 5 factorial divided by 5 minus 0 factorial times 0 factorial, which of course is 1, times the probability of a success is 1/6 to the x degree, which is 0 in this case, because in this particular question we're talking about the probability of 0 threes. So we'd have 1/6, or 0.1667 to the 0 power, times the probability of a failure, in this case 5/6, or 0.8333 to the 5 minus 0, or 5 power. Now that would result in 0.402. If we did the same thing for when x equals 1, n, of course, is the number of trials, so n will stay the same. 1 then would replace 0 from the last calculation, wherever x is. Coincidentally, in this particular example, the probability of getting 0 is the same as the probability of getting 1/3. However, after that, the probabilities change. So here we've created our entire probability distribution. So a couple things to keep in mind. Each of the probabilities should be between 0 and 1, like we said when we were talking about the general probability distributions. Also, if you add all these probabilities up in our probability distribution, you should get 1, give or take a little bit due to rounding. Create a probability distribution for flipping a coin 10 times and counting the number of heads. So we'd have to play the same game in order to create the probability distribution. Consider all the different possible number of heads that could come up when we flip a coin 10 times. We could get 0 heads, 1 head, 2 head, 3 heads, 4 heads, on and on and on, to a maximum possible number of 10 heads. Now you may notice something about this probability distribution, in particular, that it is exactly symmetrical. So the first and last probabilities are 0.001. The second and second to last probabilities are 0.01. The third and third to last are 0.044, etc., etc. So this has a bell-shaped curve that we're familiar with. Now we've referred to this as a normal distribution in the past, but we're actually going to stray away from that, because a normal distribution, we're going to talk about in the next chapter, is very specific and refers to a continuous probability distribution, whereas these are discrete.